Hi dear students, welcome to our new lecture, lecture number 6. We will study the remaining part of chapter number 4 of Principle of Concrete Structure Design. Before going to start my lecture, I am going to ask you the same question. If you have any problem, any misunderstanding, anything that you didn't understand in the previous lecture, in the yesterday's lecture related to PCSD of chapter number 4, or any point of the remaining the previous lectures 1 to 3 of PCSD, then you can ask me right now. Any one of you, do you have any question, any problem? Mr. Bruceman, do you have any question, anything you didn't understand?
No.
No? Okay. Let's continue. If you remember in our previous class, we have just started our chapter number 4 and we have studied that the different types of supports and which we are using in our building design. That there are basically 4 different types of supports: roller, simple, hinge, fixed. This is just the revision for the yesterday's lecture. There are 4 different types of supports which we are using in our building design, that are roller, simple, hinge and fixed. Okay. This is the demonstration of roller support. You can see the different 3 pictures for roller support. These are the roller supports. Okay. And simple support, you can see simple support is, this is an example of simple support. This is an example of simple support. You can see this beam is simply supported because of one wall and one column. So this type of beam is called a simply supported beam. Hinge support, you can see this type of support is an example of hinge support. This is an example of fixed support. So the same thing, I guess Mr. Fario give me the answer. This type of support is called as also a fixed support. Support their attachments and reactions. So roller support can only resist vertical force. Pin or hinge support can resist 2 forces, one horizontal, one vertical. Okay. Fixed support can resist 3 forces, one horizontal, one vertical and one moment. Okay. This is the free body diagram of the same forces. What beam actually exists, it is an structural element which is primarily resist loads applied laterally. This is a structural member which is designed for lateral loads. Please keep it in mind, it is a structural element which is designed for the loads, for the lateral loads. It usually fails in bending. You can see when the load applies, it can bend. So the failure mode is usually a bending. And because of the loads applied, we can create reaction forces, shear force and bending moment diagrams. So we will study in today's lecture about what does reaction forces do, how to create shear force and bending moment diagrams. We have also studied in the previous class that there are 6 different types of beams: cantilever, simply supported, overhanging, continuous, fixed, ended and prop cantilever. This is a free body diagram of the same beams. there are different types of members which are designed for different types of loads. Like column is usually designed for point load. Beam is usually designed for uniformly distributed load. Slab is designed for area load. Similarly, this type of structure, a varying structure, is designed for varying distributed load. Area load is the example of area load are the storage of sandbags, pyramid, making a pyramid on a slab, or moment and couple. I've already explained what does moment and couple mean. Moment is the force multiplied by its perpendicular distance. Similarly, the couple is also do, but in this case, in case of couple, there will be two types of forces. Two forces will be applied in the same direction. From here, this is the new lecture. From this slide, we are moving towards the new lecture. Today's lecture. Okay, free body diagram. Do anyone have any question, Mr. Charlie, William, Bill? Any one of you? Do you have any question in the previous lecture? I have just revised it with speedy because it was a revision. So that's why I have finished it within 5 or 10 minutes. Do you have any question in the previous lecture of PCSD? No? Okay. Let's continue. Free body diagram. Free body diagram means this diagram is with body and this diagram is without body. We are not using any body. So, free body diagram of different types of loadings on a beam. This is to be considered as point load. You can see this is a beam which is simply supported beam. One side is a roller support and one side is a hinge support. A kind of a body is applied on the center of the beam. This is to be considered as point load. Without body, let's construct this beam again. This is the point load which is applied by this body. The point load can be, the unit should be in Newton, an SI system, and if the beam is self-weight of the beam can be used as uniformly distributed load. You can see that this load is uniformly distributed on the whole beam and its unit will be Newton per meter. This type of load is called as uniformly distributed load. We also called it as UDL. It have two types of representations. We can also represent by these vertical lines and you can also represent in this way. This is also the presentation of UDL and this is also the presentation of UDL. These are just the diagrams, the difference between the free body diagram and the with body diagram. So similarly, this is a beam of varying load. You can see that the varying load is uniformly distributed on the whole beam. This is a free body diagram. If a moment is generating in a beam, then it will be like this. There is a free body diagram. If we are combining two loading like point load and UDL, then we will have to draw like this. Now, support reactions under different types of loadings. If we have applied P on a simply supported beam, you can see this is a simply supported beam. This is a simply supported beam and you have applied P on it. Okay, this P is applied on a beam in the center. This part, this length is L by 2, left side, because it is in the perfectly in the center. This P is applied perfectly in the center, so that's why left hand side, the length of left hand side is equals to L by 2, and also the right hand side will also be equals to L by 2. So how many reactions will be generated? One reaction on this support and one reaction on another side. One reaction will be over here and one reaction will be over here. Okay, so R1 will be P by 2 and R2 will also be P by 2. Half of this load, for example, it is 8 Newton. So R1 will be equals to 4 and R2 will be equals to 4 Newton. Okay. If this P is applied at an angle, if P is applied at an angle theta, it can be 30 degree, it can be 45 degree. Let's suppose, for example, this is 45 degree. If this angle is 45 degree, then what you need to do, you have to resolve this force first and then you can make the reactions. See on the board? If P is applied at an angle of, for example, 30 degree or 45 degree, let's suppose this is 45 degree. Can you see that? Just open the board screen. Then what you need to do, and the next step you need to resolve it into forces. This force can be resolved into two components. These will be two components. This will be considered as Px and this will be considered as Py. Okay, so now there are two forces, Px, Py, and how many reactions can be generated from it? What will be R1? What will be R2? Mr. Bruce, what will be R1 in this case?
Two half of the PY.
Of Py. So Py by 2, Py by 2, and we also know that roller support cannot resist any horizontal force, but hinge support can resist the horizontal force, and there will be one more reaction. That reaction will be a horizontal reaction, right? There will be R3, we can name it R3, and it will be Px. Clear? Original applied force, the reaction force. Reaction force will be opposite to the original applied force. Clear? Yes, Bruce man. Anything that you didn't understand? Do you have any questions? Okay. So you can see R1 is Py by 2, R2 is Py by 2, and R3 is considered to be Px, the opposite of this Px. Clear? Similarly, if the UDL is applied on a beam, the length of the beam is, for example, L, then the reaction in case of UDL, it will be WL by 2, and reaction 2 will be WL by 2. Clear? If there is a moment applied on a beam, in case of moment application, a moment is applied in the center of the beam, then this part of the beam, the length of this part is L by 2 and L by 2. The reaction in this case will be M over L and M over L. R1 will also be M over L and R2 will also be M over L. But remember these signs. This is downward, this is upward. Because of this moment, these directions can be changed. If this is downward, then this must be upward. If R1 is upward, then R2 will be downward. If R2 is upward, then R1 should be downward. Clear? Load diagram, shear force diagram, and bending moment diagram. Let's draw. This is a simply supported beam. A P is applied in the center of the beam. The left hand side is, the distance of left hand side is L by 2 and the right hand side is also L by 2. The load diagram can be with the reactions. It is clear that at one support the reaction 1 will be P by 2 and for another support reaction 2 will be P by 2. Clear? Mr. William, are you understanding? And because of these reactions, we can draw shear force diagram. Let's write shear force diagram will be because of these reactions. P by 2 and the positive because of this reaction, and you see that it is upward, so it will be on the compression side of the beam, so that's why it is positive. And then P is applied downward, and then P by 2 again it will be in the negative side of the beam, the tension side. So bending moment of the diagram can be calculated by the area of the shear force. What is the area of the shear force? P by 2 multiplied by L by 2. The area of the shear force is equals to the bending moment. So P by 2 is multiplied by L by 2, which gives you PL by 4. Clear? It can be drawn in two ways. If you want to draw it in tension side of the beam, then it will be drawn downward of the normal axis. If it is drawn on the compression side, then it will be drawn upward of the normal axis. Clear? And do you know what are the tension and compression part of the beam? See, for example, this is a beam. For example, this is a beam. It is not good enough, but this is the beam and this is the cross section. This box is considered to be a cross section. And your skis are embedded inside it like that, in this way. Okay. Let me draw the cross section only. the beam, this bottom part of the beam will be called as tension part. Tension zone. And this upper part of the beam will be considered as compression zone. Clear? This part of the beam, this bottom part of the beam will always be considered as tension zone, and this upper part of the beam will always be considered as compression zone. Clear? Do you have any question? Good friend, do you have any questions? If no, then let's continue. Did you understand? These are the general guidelines. It is quite important. For example, if these are the different beam types. All beams are simply supported or with different types of loading. If the load is point load, then what we can say, shear force will be constant in this way. This will be the shape of shear force, and moment will be on the compression side, like positive side, and it will be considered as linear line. This line will be linear triangle line. Okay. If the beam is supported by UDL, uniformly distributed load, then the shear force will be a linear diagonal line of a beam. So shear force will be linear triangular line, and its moment will be a parabolic 2-degree curve. Similarly, wearing load, this is a wearing load. This beam is subjected to a wearing load. Its shear force will be, the line of shear force will be parabolic. You can see this line will be parabolic. If this line is parabolic, this line is parabolic. You can see if it is parabolic, then this moment shape will be cubic. The curve will be a 3-degree curve. It will be cubic in nature. Similarly, if pin or hinge supported inside the beam, then shear force will be constant, or rectangular in shape, and its bending moment will be in this way. It will be also be a linear. If this is cantilever beam. If this cantilever beam is subjected to point load at one side, this is fixed support, this part is fixed support, and the load is applied on another side. There is no support in this way, in this side. So in this case, again, the shear force shape will be constant. It will be rectangular, and moment will be linear, but the shape will be like this. This type of triangle will be generated because of this moment. And if the same beam, cantilever beam, is subjected to uniformly distributed load, a UDL, then shear force in such case will be like this way. It will be a triangle, and the line of the triangle will be linear, and its moment will be parabolic. You can see this line will be a parabolic in shape. There are the few steps to draw load diagram, shear force diagram, and bending moment diagram. The first step is draw support reaction. First of all, you need to draw the reactions. Then calculate support reaction using equilibrium conditions. Then find the values of those reactions. First step is draw the support reactions. You need to draw the reactions, and then you need to calculate the values of those reactions. you need to calculate the values of reactions by using equilibrium conditions, and then calculate the shear force at the point of loading by taking beam section up to point of concentration and using equilibrium condition. Means in the third point, in the third step, you can calculate shear force. The third step is to calculate the shear force, and in the fourth step, calculate bending moment. You need to calculate bending moment, and bending moment can be calculated as the area of the shear force diagram. Simple ways. Then we can draw load diagram, shear force diagram, and bending moment diagram by using these values. The values which are calculated in step number 2, step number 3, and step number 4. And step number 2, you need to calculate the reaction forces. Clear? And then in step number 3, you need to calculate the shear force. And in the step number 4, you need to calculate the moment values. Because of these 3 different types of values, you can draw load diagram, shear force diagram, and bending moment diagram. Okay. Mr. Bell, are you understanding?
Yes.
Dragon, do you have any question, Mr. Dragon?
No, I don't have question.
Okay, let's continue. These are the different sign conventions of a beam. Try to understand these sign conventions. Listen, internal reactions of a beam required for equilibrium. If I cut a beam from the center, this is the left side of the beam and this is the right side of the beam. Normal force will be denoted by N, shear force will be denoted by V, bending moment will be denoted by M. Okay, so you can see that this is R1 reaction. This distance can be called as X. I have denoted it with X. And shear force direction will be downward, normal force will be in the rightward, and moment will be upward, anti-clockwise. We also called it counterclockwise or anti-clockwise. And if we are considering the right side of the cut, then it will be, this length will be L minus X. This is reaction 2, and over here all these sign conventions of reaction, the forces reactions will be different as compared to the left side of the cut. Like in left side of the cut, the direction of the shear force is downward, but over here it is upward. Normal force is in the right direction, but in this case it will be in the left direction. Moment is anti-clockwise, counterclockwise, but over here moment will be clockwise. Okay, so these are the different sign conventions when we are considering forces in one direction of the beam in one direction. Then for another side of the beam we will use opposite direction of the forces. There are few formulas which we need to be used for beam design. Concepts and formulas of reinforced concrete beam design. There are few concepts involved in it. Let's start from it. That loads like dead load and live load. These are the different two types of basic loads. loads, dead and live, bending moment and shear force diagram of concrete beam shown as below respectively. If this is the beam, like this is overhanging beam. From this side, this is overhang. This side is the clear span, and this is overhang. And this beam is subjected to a uniformly distributed load. Then the shear force shape will be like this. This is the shape of the bending moment. This is for bending moment diagram, and this is the shape of shear force. This is SFD diagram, and this is bending moment diagram, BMD. Dear students, your call will be disconnected automatically because the first section of the class is completed. The 40 minutes are completed now. Within few seconds, your call will be disconnected. After a few seconds, please join it again. If you have any question in the meantime, please ask me. Any one of you, do you have any question? Yes, dear students, till now, do you have any question? Any one of you? So Charlie, do you have any question?
No, no question.
Okay. We were talking about the concept and formulas of reinforced concrete beam design. We will study few formulas over here, and then we will use these formulas for beam design. How to design a beam? We will use these formulas, and the same technique you will have to use the same formulas for the beam design of your project. I have assigned you a project. You have to solve all the beams of those that project. There are 8 different beams in that project. You have to design all the beams by using these formulas. So try to understand the formulas. Let's study them. Loads like dead and live, bending moment and shear force diagram of concrete beam as shown below respectively. You can see here, this is a beam. This beam is called as overhanging beam. A uniformly distributed load is applied on this beam. This beam is subjected to UDL load, uniformly distributed load. This is the shear force diagram, and this is the moment diagram. You can see this is the shear force diagram. This is the moment diagram. Over here, because of this force, the bending moment, the shear force is upward. This is positive. This will be considered negative. This will be the positive part. This will again negative part. It starts from 0 and it ends at 0. Where the shear force is 0, this is the point where the shear force is 0. Over here, the bending moment will be maximum. The moment value at this point will be maximum. Shear force is positive inside, so the bending moment will be negative. And again, shear force is negative, then it will move towards the positive zone. Then again, it is positive, then it will move again towards the negative. If it is negative, then it will move again towards the positive zone. Clear? So this is the diagram of uniformly distributed overhanging beam. You can see that the shear force will be drawn in this way and bending moment will be drawn in this way. This is just a demonstration. Failure modes and reinforcement. Try to understand it. Concrete is assumed to resist compression only. We assume that concrete is a brittle material, so that's why it can resist only compression load. It can only resist compression forces, compression load. Okay. Tension shall be resisted by reinforcements. Concrete resists compression and tension resisted by reinforcement. Okay. Reinforcement shall be placed at the side of the beam that has tension. As I have shown you on the board, for example, you can see, turn on my board picture, you can see the bottom part will be tension zone, and this upper part of the beam will be considered as compression zone. This part, if I cut this beam from the center, this bottom part will be considered as tension zone, and this upper part will be considered as compression zone. Clear? So, for simply supported beam, tension is at the bottom of the beam, while for cantilever beam, tension is at the top of the beam. If it is subjected to uniformly distributed load, or if it is subjected to a point, or if it is subjected to a point load B, this is the complete length. So the bending will be in this way, means your beam can bend in this direction. Beam can bend in this direction. So this is the bending part of the beam. Load is applied in the center, so beam will be bent. And this way. This is simply supported beam. We call it simply supported beam. But if the beam is cantilever beam, do you know what type of beam is cantilever? It is again subjected to P load, point load. What will be its bending part? Again, if P is applied on this beam, then the shape of the beam will be bent in this way. It will be bent in this direction. So we can say that tension and simply supported beam, tension is in the bottom, this part, part is creating tension. So we can say that tension at bottom. But over here, this part is creating tension. So we can say that tension is at top. So in case of simply supported beam, tension part will be at the bottom, but in case of cantilever beam, tension part will be on the top. Clear? Remember this thing. So that's why you can see that. And simply supported beam, tension will be at bottom. Clear? And for cantilever beam, tension will be at the top. Clear? So shear, second part of failure mode is shear is at its maximum at the edge supports, and diagonal shear cracks are normally developed close to the support. I will show you the picture of diagonal cracks. Like these are the failure mode. You can see that diagonal cracks, these are called shear cracks. You can see that these are called shear cracks. Shear cracks are always close to the support. This is the support. Shear cracks will always near to the support, and these are the flexural cracks which propagate vertically. These are flexural cracks which propagate vertically, and usually it generates at the center of the beam. Clear? So that's why we need to provide the shear reinforcement or stirrups closely spaced near the supports, but we can provide more space between the stirrups in the center of the beam. Clear? So shear is at maximum at the edge supports. Shear is maximum at edge supports. Means shear force will be maximum at near the support. Shear force will be maximum. Shear force will be maximum at this support. Diagonal shear cracks are normally developed close to the support. These are the diagonal cracks. Diagonal cracks. It is diagonally propagate. So diagonal cracks propagate near the supports. Stirrup for shear reinforcement is normally placed vertical to the to intercept the crack. Stirrup for shear reinforcement is normally placed vertically to intercept the crack. To control these cracks, these diagonal shear cracks, we provide shear reinforcement vertically. These lines demonstrating the shear reinforcements. These are basically the shear reinforcement. Shear reinforcement will provide vertically. Clear? They are normally closer space near the support. As I told you, we need to provide the close spacing, the small spacing between stirrups near the supports. But in the center we can increase the spacing. They are normally closer spaced near the supports. It is normally, these stirrups are normally closer spaced near the support, are gradually spread out toward the center of the beam. We take more space spread out towards the center of the beam. Closer space at near the support and spread out towards the center of the beam. Clear? By taking this important we can move towards the formula. Do you know this is called as Whitney stress law? Have you ever studied Whitney stress block, Mr. Charlie? Do you know? Have you ever studied Whitney stress block?
I don't know.
This diagram is basically a Whitney stress block. Clear? So let's study this diagram. This is a Whitney stress block. Whitney was a scientist. This is the name, and this diagram is proposed by the name of this scientist who proposed this Whitney stress block. He was a good researcher. Design assumption: strain distribute linearly across the section. Strain is distributed linearly across the section. Concrete resists only compressive stresses. These are the assumptions. Therefore, the stress distribution across the section of the beam is as shown below. See on the board. Whitney stress block showing up, for example, this is your beam. For example, this is your beam. We always consider this cross section of the beam. Let's draw the cross section of the beam. The steel is predominantly in this side. This part of the beam will be considered as tension part, and this part of the beam will be considered as compression part. Let's draw a normal axis. For example, this is a normal axis. Got it? Normal axis. The bottom part is tension, and this upper part is compression. Whitney says that this will be the elongation because of this. For example, this is the shear force diagram. This will be the elongation. For example, let me show you over here. Then I will come back to the strain diagram. This is strain. But let me draw the stresses diagram first. This is compression stresses. call it C, and this is tension part, we call it D. Clear? Or you can use a different sign convention, like for example, if I use it as C, or if I use in this direction as C, it depends on your choice. But Whitney says that, for example, this is the compression part, this is the tension part, this stresses will be compression force in this direction, tension force will be generated in this direction. Because of this compression force, this type of shear force will be generated, and because of tension force, this type of shear will be generated. And because of these forces, a moment is generating in this direction. And all these things will be studied in few formulas. And this, the distance of this width of this beam, that is called as small b, and this depth of compression part, we also call it as small a. Remember these things. Clear? So our complete discussion will be based on this part. This is compression part. Try to understand. This is compression part. This is tension part of the beam. The width of the beam is a small b. Because of this beam, this is the strain generating because of these beams. Because first, we are moving towards the stresses. Compression part will generate compression force. Tension part will generate tension force. Okay. So, because of this compression force and tension force, this strain is generated. Because of this strain, epsilon, we denoted by epsilon. This strain is generated, and because of these things, these forces, a kind of moment will be generated and being clockwise. The depth of this compression part will be equals to small a. Width of the beam is small b. Our complete formula will be around this picture. So let's derive the formulas first. At an ultimate strain, the ultimate strain that a beam can take, that is 0.003, the stress at extreme fiber of the beam, which is the ultimate strength of concrete, that is Fc prime, means at ultimate strain, the final strain, the maximum elongation that is possible in a beam, that is 0.003. At this strain, the concrete will attain its maximum compressive strength, that is equals to Fc prime. It can be 3 ksi, it can be 4 ksi. The distribution of the compressive stresses is a complex curve. For calculation purpose, a stress block of 0.5 Fc prime spread over a depth A. This is the small depth A. Therefore, the total compressive stress is a rectangular beam. We usually call it this formula, this C force. This C force can be calculated by using this formula. Compression force can be calculated by this formula. 0.85 FC prime AB, where small b is the width of the beam as it is shown. Clear? And this NA means neutral axis or normal axis. Similarly, at ultimate stress situation, the concrete at top portion of is subjected to compression. At ultimate stress part, as we have studied, at ultimate strain, concrete is attaining FC prime. But similarly, at ultimate stress situation, the concrete at top portion is subjected to compression. The compressive stress distribute uniformly over a depth A. The resultant of compressive stress C is located at a distance A by 2 from the top surface. The tensile force is taken by rebars at an effective distance D from the top surface. By equilibrium, the tensile force is equal to the compressive force. This is T will be calculated by this formula. T equals to ASFY. AS means area of steel, Fy is the yielding strength of steel. C can be calculated by 0.85 Fc prime AB, where Fc prime is compressive strength of the beam, A is the depth, small depth over which the compressive stress are distributed, and B is the width of the beam. Clear? So all these things are well known, and it is clear from this status that by equilibrium, from this paragraph we are considering that by equilibrium condition, the tensile force is equal to the compression force. So T is equal to C. So ASFY is equal to 0.85 Fc prime AB. So that's why just rearrange this equation. Just rearrange this equation for small a. So I have just rearranged the equation. This will be the new form of the equation. Just divide this equation with a small d. So it will be formed in this way. This will be the new form of the equation. As you can see, Fy is basically the yielding strength of reinforcing steel, and As is the area of steel. Okay. Why we have divided this equation with a small d? Because we are incorporating reinforcement ratio, where reinforcement ratio is equal to area of steel divided by BD, where B is the width of the beam, A is the area of steel, and D is the effective depth of reinforcement. And I will explain what does effective depth means. Or even I can show you right now. For example, this is a beam cross section. This is your steel. From the center of this steel to the surface top, this distance will be called as small d. This small d is equals to from top surface to the center of the beam. This is called as small d. We also called as effective depth. Okay. So because of if rho is equals to ASBD, so this equation will form and this form. The equation will be changed in this form. So for example, if M is equals to this equation, then A will be rho dm, the nominal moment strength of the section, and nominal moment section can also be called as C d minus A by 2, where 0.85 Fc prime AB d minus A by 2. This is equals to, this part is equal to C, and d minus A by is a perpendicular distance. Where I have encircled this formula because we will use this formula in our numerical calculation. The nominal moment strength of the section can be changed to this form ASFY d minus a by 2, it can be also be formed in this form, and it can also be written in this form, where ACI code requires that the factor moment should be, this factor moment should be less than or equal to phi mn, where phi mn is, mu is the factored moment, mn is the nominal moment which can be calculated by this formula, and phi is the strength reduction factor, where for beam, in case of beam is a tension control member, we need to use phi equals to 0.9 as a strength reduction factor for beam, and the area of the reinforcement is area of steel equals to rho BD. We will also use this formula in our beam calculation. Similarly, you can see the strength control section, that is beam, which is equals to phi equals to for beam, that is 0.9. We have already studied this table in the previous lecture, in the previous chapter, chapter number 3. We have already studied this chapter. It is available in SCI code, table number is 1.3. These are the strength reduction factors for different structural members. Okay, these are the formulas which we will study, and few more formulas which we will have to use in the beam calculation. That if, for example, let mu is equals to phi mn, then mu can be calculated. This is the formula of the actual formula of mn, the nominal moment. I am using this formula, this nominal moment formula. These are the formulas of mn. You can see this formula is using here. So mu equals to phi mn. This is the formula of mn. Divide both sides by dd square. We have, this is the new formula, and this will be the finalized form of this equation, where Rn, if Rn is equals to mu pi dd square, and we can rewrite this equation in the form of Rn. Solving this equation, the reinforcement ratio will be used in this form. So these are the formulas which we will use, like reinforcement ratio will be calculated by this formula, Rn will be calculated by this formula, mu should be less than or equal to phi mn, mn formula is this one, area of steel is ratio over here, and steel reinforcement ratio is this one. All these are the different formulas which we will use in the problem solving. Let me finish this topic too. There are 3 different types of failures available. One is called ductile failure, another is called brittle failure, and the third one is called balanced failure. When steel fails, when reinforcement fails, then we can say that the failure is ductile. When concrete fails, concrete crack, but steel is still in a working condition, then we can say that this failure is called as brittle failure. There are 2 situations when reinforcement concrete beams fails due to bending. One is, this is the one condition. One is when the reinforcement steel reaches its yielding stress, that is Fy. And the other is, another condition is when the concrete reaches its maximum compressive stress. When reinforcing steel its yielding stress, this will be called as ductile failure. When this concrete reaches its maximum compressive stress, then we can call it this will be a brittle failure. When a reinforcement concrete beam fails in yielding of steel, the failure is ductile, as I have explained, because the steel can stretch for a long period of time before it actually breaks. When it fails in concrete, when the concrete fails, the failure is said to be a brittle failure because concrete breaks when it reaches to the maximum strength. But when these two things fails together, like beam, steel reinforcement and concrete fails together, reach a maximum strength, then in that condition the failure will be called as balanced failure. When concrete reaches its maximum strength, at the same time steel reaches its yielding stress, it's called as balanced condition. Use maximum strain, that is 0.003. This is the maximum strain of a beam concrete, and assume a linear distribution of strain across beam section. One can determine the reinforcement ratio at the balanced condition. The reinforcement ratio based on ACI code is in case of balanced condition, we can use these formulas to calculate the reinforcement ratio in case of balanced condition. 0.85 C prime over Fy beta 1 87,000 divided by 87,000 plus Fy, where Fc prime and Fy are in PSI. PSI means pounds per square inch. This is FPS system, and this is a formula which is in megapascal. Megapascal means Newton per Pascal is mega. This is mega. Mega is always here. Newton per meter square is equals to Pascal. This is SI system, where beta 1 value is 0.85 for 4000 psi concrete and 0.05 for reach of 1000 psi excess of 4000. So the behavior of reinforced concrete beam can be shown in this picture. This A, B and C. This A part is the load distribution curve over here. Then this beam is showing the as I have told you, this beam is showing the tension part, and the upper part is the compression part, and this from the center of the steel, this is called as small d, which is also called as effective depth. B is the width of the beam and h is the height of the or thickness of the beam. These are the demonstration of this C part is the demonstration of strength difference because of these stresses generated inside the beam. Well, from my side, this is all over. Do you have any question? If you have any question, please ask me, because this is the last minute of this section. After a few seconds, your call will be disconnected. Please join it again so that I can mark your attendance. Do you have any question, dear students? Please join the call again. Well, these are the few basic formulas which we will use. Which will be used in the design of a beam. We will use these formulas in the design of a beam. Do you have any question in this complete lecture? Mr. Bruce Wayne, Dragon, Mr. Bell, Mr. Charlie, do you have any question? Mr. Bell, obviously I know these formulas, the derivation of formula is quite a boring thing, but You will understand these formulas when we will use these formulas in the problem solving. When we will solve a numerical related to these formulas, then you will be able to clear similar things, similar feelings as we will feel about the soil mechanics and foundation course, that we have studied 13 different relationships first, and then we have solved 10 numericals on those formulas. Well, do you have any question, any one of you? Mr. Charlie?
No, no question.
Question. Mr. Dragon?
Hello, teacher.
Do you have
I
any
think
questions?
these formulas are difficult for me. I maybe need some time to study it.
Okay, for your better, I know this course is a little difficult, and one more thing, it is an English language. You have to study in English. So that's why after delivering of my lecture, I am creating a video for you guys, and also I am providing you PPT, all the lecture notes, everything is provided, and even I am also available every time. If you have any question, you can directly ask me. Okay,
Okay, I see.
Mr. Bell, do you have any question?
No question.
Till now, obviously this part was a little difficult, but it's quite important related to your beam design. Your beam design is purely based on these formulas. We will use these formulas and beam designing. So please memorize these formulas if you are not understanding. How many students have joined? 77 students, 77 participants are available right now. Let's wait for them for 2 or 3 minutes, so that after that I will mark your attendance. Mr. Bruce Wayne, do you have any question or any suggestion to improve my teaching quality?
No.
Nothing. Okay. Where is Miss Granda? Is she absent today? I cannot find her. Yes, I have found her. She is available, but her camera is off. Mr. Kevin, Tim. Okay, please join. How many students right now? 82. Okay. I'm going to mark your attendance. After that, you all will be free. Let me mark your attendance. There are 82 participants available right now. that, dear students, I am marking your attendance. Okay, done. Thank you. If you have any question, you can ask me anytime. The class is going to be end now. Thanks for your presence. See you in the next lecture. Bye-bye, dear students.
See you, teacher.
Have a good day.